This does not look nor sound right. Let's fix it. Let's start with what it is. I need an antenna rotator to track satellites. I doubt that my homeowners association will allow me to put a big antenna into my backyard. I need a more nimble solution. There are a few options. Yaesu sells beautiful tracker units, but they're a bit pricey for me. The Kraken Discovery Drive is a new turnkey product, but I prefer having full access to the hardware and software. Gabe from Save It for Parts has been abusing Winegard mobile satellite dishes with great success. And then there is the SatNOGS rotator project. It has been around for a while and is completely open source hardware and open source software. The plans, schematics, instructions and the firmware are all available online, though the project can be a bit confusing at first. Let's start with the SatNOGS rotator control board. There's a website and multiple Git projects dedicated to this controller. The board is available as a KiCad project, but the KiCad version is a bit dated and some components are nearing end of life. I used the opportunity to upgrade the project to KiCad 9, which is available for the currently stable Debian distribution. Yes, I mostly use Linux for my daily work. I am thinking of adding peripherals and maybe a Raspberry Pi to my setup, and I feel more comfortable with a proper 5V rail instead of relying on the Arduino for power. I also changed out some connectors and dropped the RS485 option since I can always use a transceiver breakout board. So I ordered 10 PCBs from JLCPCB for $5 plus shipping and tariffs. I sprang for DHL delivery and just a few days later 10 perfect boards arrived at my doorstep. Thanks JLCPCB. I uploaded my bill of materials to DigiKey, followed their advice to buy a few extra components to save money, and a few days later everything arrived in the mail. I wanted to use my PNP machine but didn't have feeder trays for 16 and 24mm tapes. I used Pat Deegan's Open SCAD generator to create these trays and printed them out in my Bamboo Lab P1S. I'm getting so much use from this little machine. The first task was to load the tapes into the trays and tell OpenPNP where to find the components. Placing the full trays is so simple thanks to the locating pins dropping into the fixture plate. Previously, I used a Python script that assigns components heights from their step files in KiCad. For passives, I noticed the heights were generic, while actual heights varied. If the heights are wrong, components get swished onto the PCB or dropped from above, so I corrected the component heights using the datasheets. I cleaned the board with isopropyl alcohol and applied solder paste. I still don't have a feel for the right amount. On one board I applied too much, which can cause solder bridges on microchips. On another board I applied too little, which caused components to move during placement. I also noticed the paste seemed to dry out on the boards. I guess the flux evaporates quickly. The board on its mounting plate is dropped onto the fixture plate. Now we need to tell OpenPNP where to find one corner of the board, and the software will use the fiducials to locate and orient the board properly. OpenPNP picks up the first nozzle tip without problems. But the second tip must have shifted forward in its holder because the nozzle hung up on the tip and the head belt ratcheted. I rehomed the head and decided to mount nozzle tips by hand for today. The actual pick and place process worked nearly flawlessly. I did forget to peel some tape covers, and the cameras caught a few 0805 components that had flipped inside their tape pockets. But otherwise, the process worked fine. The dance of the nozzle still feels like a miracle. Since the board exceeds the size of my little heating plate, I had to use the bigger one. My small plate has 3 custom temperature settings that I set to 150, 235 and 250 degrees Celsius. First I soak the board for a minute or two at 150, then I flow it at 235. The big plate only allows setting a single temperature, which means reprogramming it after the soak. Not ideal, but it works. Given the excess solder paste, some components shifted and rotated, and I had to use tweezers to correct their placement. Some components require hand soldering. One big capacitor is through-hole, so I solder and clip its leads. For reasons lost to time, I put the I2C pull-up resistors on the back. If I ever do another iteration of this board, I will replace this capacitor with a surface mount part and move the pull-ups to the front. While I'm at it, I also placed the headers on the Arduino Pro Mini. Time to test the board and power it up with my benchtop power supply. Unfortunately, when I turn on power delivery, the supply immediately resets to 0 volt and 0 amps. After some testing, I conclude the unit is busted. These units have a Schottky diode, 1 or 2 field effect transistors, and a relay that switches the actual power stage. I suspect that one of these parts failed. We can troubleshoot the unit in a later episode. For now, I simply order a new power supply. With overnight shipping, we're back in business and can test the 15 volt input, the 12 volt output and the 5 volt output. All good. Now we can also calibrate the stepper drivers. We're using the DRV8825. I want to limit its current to 1 amp, so I adjust the potentiometer until I read half a volt between the Viper and ground. After a bit of fiddling, we're close enough. We can now attempt to build the firmware. Let's go to the GitHub page, download the project, download the 2 dependencies, set up the makefile and build. The GitHub page also lists the EasyCom commands we'll later use to test the board and firmware. I had no luck flashing the Arduino using the automatic RST-DTR method with my FTDI cable. Then I remembered that I own a tiny AVR programmer and managed to override the default Blinky program with the SatNOGS control software. But the programmer will be inconvenient for updating the firmware in the future. I decided to give the FTDI cable another shot, but this time I abandoned the automatic RST-DTR method and tried the manual reset option. Lo and behold, I managed to release reset at the right time and the firmware flash succeeds. Time for testing. The controller responds to the VE command requesting the firmware version. The yellow motor works both forward and backwards. The pink motor, however, just vibrates. To troubleshoot, I switch motors and controllers and tested voltages. All fine. The most likely remaining cause is the cable. I used my multimeter to check continuity and found that 2 wires were indeed swapped. Let's swap these wires. The controller still responds to the VE command. The yellow motor turns, and the pink motor turns. Success! I now have a working controller. I will put my KiCad project onto my GitHub. The link to my GitHub and the other sites that I used are listed in the video description. My next step will be building the mechanical SatNOGS unit. Stay tuned for that build. Thanks for joining me at 4111 Spyglass. See you next week.